All right, so cool, that's downloaded. Get rid of this. And we will pick up where we left off, although I also want this one. So we'll work through a few examples from where we left off on Friday, and then we'll jump in and do some Excel work to kind of end the class. I'll then briefly kind of introduce the next topic we're going to start talking about for the rest, well, probably this weekend, next really. So we left off kind of saying, what happens if we have an example where we don't know what the population variance is? So all we have is a sample variance. We can still build our confidence interval. We said the only issue is going to be if I was to turn this into like a z-value, because I only have the sample variance, my standard deviation of my sample means, if I divide by that, won't quite give me a z-value. It's going to give me something that comes from a student t distribution. Right? So we have to use these t values from a student t distribution, and each degrees of freedom, or each sample size, right? The degrees of freedom is just n minus 1, sample size minus 1, will have its own distribution. So there's a bunch of student t distributions. Which one do we use? We first have to identify the degrees of freedom to figure out which one we want to use, and then find the t-value from that distribution that gives us alpha over 2 in the tail. So we briefly looked at that student t table last class. We'll look at it again today for a couple examples. So we still build the confidence interval around our sample mean. Now, instead of having a z-value that tells us how many standard deviations away to go from that sample mean, we'll have a t-value, which still represents how many standard deviations away we want to go from that sample mean. We'll then multiply that by our sample mean. But it's, sorry, not our sample mean, our sample standard deviation, but it's the sample standard deviation of our sample means where we're using that sample variance instead of the population variance. Okay? So this is kind of where we left off. We had these steps of how we find confidence intervals. It's the exact same thing we've been doing for sample means. It's just now instead of using a z-value or the standard normal distribution, we use the student t distribution or a t-value. Okay? And of course, we're using a sample variance instead of population variance. Okay? But everything else is going to be the exact same kind of format. So we had this example, and this one doesn't have a lot of context, but just to put some numbers to this, and then we'll go through something with a little more context. Let's say I take a sample, whatever the variable I'm interested in, I take a sample of 36, I find a sample mean of 9, and I calculate from this sample a sample variance as well of 324. If I wanted to build a confidence interval for the population mean that corresponded to the alpha of 0.01, what would it be? So first of all, at an alpha of 0.01, my confidence level would be what there? So 0.01, that was a confidence level of, 99%. Right? So I identify the pieces of information I need right away, right? I'm always given this, right? I'm given the sample mean, the sample size, the sample variance. Alpha here we were given, but if I instead had said, build me a 99% confidence interval, you would have known that alpha should have been 0.01, or we can work in either direction there. But what part of the confidence interval equation I need is this t-value, right? So here, my degrees of freedom, if degrees of freedom is n minus 1, right? My sample size is 36, so 36 minus 1, my degrees of freedom is 35. The alpha that I was using was 0.01, so the area I want on either side of my confidence interval is alpha over 2, or 0.01 divided by 2 is 0.005. Okay? So I go to this t-table. I know that the area I want in the tail, if I scroll up here, is 0.005, right? So this represents the area that I want in one of my tails, right? So alpha over 2. So 0.005, and then I go degrees of freedom 35. The t-value at a degrees of freedom of 35, that gives me 0.005 in that upper right tail, is 2.724. Okay? So that's the value that I'm going to use. It's a little bit easier than when we were doing standard normal distributions, because now when I look up alpha over 2, it already instantly gives me the positive value, because it's only kind of looking at that upper right tail. So 2.724, that's going to be the t-value that I use. So I can do the intermediate step where I calculate that standard deviation of my sample means, plug in my values here, and from there it's just a matter of plugging everything into that confidence interval equation, adding my margin of error to get the upper bound, subtracting my margin of error to get my lower bound. then I can kind of write my confidence interval like this, right? It goes from 0.84 to 17.16. Okay? Now here, where I have this part of my confidence interval, right? I'm going to show you something. So really what I'm doing there is we start out, this is how I build my confidence interval. But I know that this, the standard deviation of my sample means, is actually just the square root of my sample variance over my sample size. Another way we could write this, depending on what information I'm given, is the standard deviation divided by my square root of my sample size. Right? All these are the same thing. Here, I kind of skip the intermediate step. Here, I first calculate the intermediate step, and then I plug it in. Really, whichever way is kind of easier for you to think about, it doesn't matter, right? They'll give us the same answer. So all just different ways of kind of writing the same thing. All right. Any questions on that? Keep moving. All right. So we got a pretty wide confidence interval here. So why is that the case? Just kind of a reminder of things we've talked about in the past. If I look at this, I have my sample standard deviation or my sample variance pretty high, right? 324 is pretty high sample variance. And so it kind of is increasing my margin of error by quite a bit. And my sample size is only 36, right? So as I take a higher and higher sample size, that decreases my standard deviation of my sample means, which would decrease my margin of error. But I don't have a very high sample size here, right? It's relatively small. Not like super small, but relatively small as some of the other stuff we'll look at. So I still have a pretty wide range of values. Okay? So let's look at an example that has a little more context. So let's say the American Medical Association, puts out this pamphlet or something that says the mean salary for physicians is $175,000. You don't think it's quite that high. You take a sample of 81 doctors and you find a sample mean of 160,000. Sorry. And you also find a sample variance from those 81 doctors of 324 million. Right? Sample variance ends up being pretty high because, right, we're dealing with a high value. When it gets squared, it goes up pretty quick. So if I wanted to find the confidence interval for the true population mean at an alpha of 0.05, which alpha of 0.05, I'm building a 95% confidence interval. I've got my sample mean. I know I'm going to base my confidence interval around that. So if I look at these values, which of these could I rule out right away? Well, it looks like 160,000 in the middle of these. But here, 160,000 is only what? 4,000 away from the upper bound, but 14,000 away from the lower bound. So C can't be an answer, right? Because our confidence interval should have that sample mean we found smack dab in the middle, right? And 160,000 isn't quite in the middle here. Right? I say it isn't quite, it's not even close. But from there, we just have to actually kind of work through this example, right? So we've got everything that we're given. So the next thing, look up our t value because we only have a sample variance. My degrees of freedom here would be what? So 81 is my sample size, so 81 minus 1, 80. Degrees of freedom of 80. My sample variance, sorry, not my sample variance. My alpha here is 0.05. So the area I want on either side of my confidence interval would be 0.05 divided by 2, so 0.025. So I go to the table, student t table. I wanted what? 0.025 in one of my tails, right, in each tail. I go down to degrees of freedom 80. And the value that I want, that the t value that would give me that 0.025 in each tail at a degrees of freedom of 80 would be 1.99. Or I want to go 1.99 standard deviations to the left and right of my sample mean to get my upper and lower bound. So if I want to go 1.99 standard deviations, I need to know what are my standard deviations to the sample mean. This is where we can calculate the intermediate step if we want to. So plug in our sample variance, plug in our sample size. We get that standard deviation. And now it's just a matter of plugging into that equation. Once again, here's if I would write it all out on one line. What I could substitute in for this guy right here was just that standard deviation of my sample means that I found on that step 3 or that intermediate step. Okay? So once I find that, It's just a matter of subtracting that margin of error to get my lower bound, and then adding that margin of error to get my upper bound. Okay. Any questions over that before we keep moving? So kind of how do we start to use these confidence intervals? We've got 100, so our confidence interval with 95% certainty, I can say the true mean salary for physicians is between $156,000 and $164,000 approximately. If the American Medical Association was saying that the true mean is $175,000, well, I can look at them and say, well, with 95% certainty, I can tell you that you're wrong, right? Because with 95% confidence, I know the true mean is somewhere in this range. So once we have these confidence intervals, you can start to think about, you can almost start to fact check things. Now, you're going to be wrong 5% of the time here when you tell someone that. But, right, with 95% confidence, you could say that that can't be one of the true values, okay? All right, any questions on that before we kind of jump in to do a little bit of Excel work here? Good with that? All right. Oh, no, I still want to stay here. I just want to. So I've got 2 slides here that kind of summarize or kind of recap what we're going to do, but let's just work through it in Excel. So let's go to that confidence interval example file, open it up. I want to go to view so you guys can see it a little bit easier. All right, so I've got female height data. I've got whether or not the individual is white or non-white. I've got their height, their weight. So what I'm going to do is I'm going to first just try to build a confidence interval for where the true population height is for females in the US, because this was a sample taken from the US. So I'm going to delete these 3 here. And something I had someone tell me that I hadn't thought of. When I'm deleting these quick, I'm hitting the delete button, and on some laptops, the delete and backspace button, if it's a smaller laptop, are actually the same button, and you have to hold shift or something. So if you only hit backspace, it's going to look like you're only deleting 1 cell. So make sure you're hitting the delete and not the backspace. Otherwise, you can only delete 1 cell at a time. Okay. So, I mean, I'm going to go over this real quick because hopefully we're okay with this now. I'm using this height variable. If I want the sample mean, I can just simply use that average. Right, take the average of that variable. So just to be a little bit more complete here, this is our sample mean. If I want the sample variance, var.s, right, select that height variable. Sample size, we use that count function. It just went through that variable and counted the cell if it had any value in it, right? So we've got our sample mean, our sample variance, and our sample size. We used those functions before. These alpha values correspond, right? 0.1 is an alpha, is 90% confidence. 0.05 is the 95% confidence level. And 0.01 is the 99% confidence level, if we're kind of just wanting to kind of keep track of this. Okay? So when I'm building these confidence intervals, one of the things that I'm going to need, or if I only have a sample variance, I need to be looking at t-values. Okay? So last week, we went over how to build confidence intervals when we had a known variance. So the variance was just given to us, the population variance. So we use that z value, the standard normal distribution. Now we have to use the student t distribution. So instead of norm.s.inv to find the z value, we'll use t.inv to return to us the t value that we want to build our confidence interval. So what area do I want kind of in each tail? Alpha divided by 2. What's my degrees of freedom? So comma, tell it the degrees of freedom. Because remember, there's several student t distributions, and I need to tell Excel which one to use. Well, that's simply my sample size minus 1. Okay? So it's going to return to me the t value that would give me alpha over 2 in that lower left tail. So unlike the physical table, the t.inv function works the exact same as the norm.s.inv, in which when you tell it a probability, it assumes you're telling it the probability in that lower left tail. Okay? So if I tell it alpha over 2, 0.1 over 2, that's going to be what, 0.05? What's going to be true about this t value is it's negative, right? Because that student t distribution that we have is still normally distributed around 0. It just had a variance that was greater than 1, right? And so I know that if I'm looking at the lower left tail here, the really small values, anything less than 0.5, right? Because the area to the left of the mean of 0 is 0.5. I'm going to be getting the negative t value. Now, let's say if there was, well, I'll keep it general. Let's say if there's alpha over 2 here, if I were to want the t value that gives me alpha over 2 in the upper right tail, when I go to Excel, I would actually not want to tell alpha over 2, but 1 minus alpha over 2, right? Because if there's alpha over 2 in this upper right tail, the area to the left of that would be 1 minus alpha over 2. So that's one way I could do it, is instead of telling it alpha over 2, because I don't want the negative sign there because that's already built into my confidence interval equation. So I could tell it 1 minus alpha over 2. So I'll type that here just to show you something here. So 1 minus alpha divided by 2. And then my degrees of freedom is my sample size minus 1. So notice it's the same value. If I try this out, you can see it's the same value, right? But this one's returning me a negative value. So I could just tell it alpha over 2 and use that absolute value function, which essentially just drops the negative sign, okay? Either way is fine, right? Either way will give me the same value. So, like I said, two different ways of doing the same thing. Now, if I want to copy this down so I can find lower bounds or build confidence intervals for several different alpha values without typing this in every single time, I want my cell reference for alpha to change, but I don't want my cell reference for the sample size to change, right? If I copy this down, notice it's going to be using K5. I want it to use K3 still. So I'm going to freeze that cell or put $signs right in front of the column row heading. Now when I drag this down, I get the t values I want for each one of these different levels of alpha. Okay. Notice, excuse me, these t values, because our sample size is so high, right? We go here, we said, well, when the degrees of freedom is 1,000, to the third decimal, a lot of the times these values don't look any different than the standard normal values, which would be when degrees of freedom is infinity. So at 3,000, we're going to be even closer. So 1.645, 1.96, 2.576. We're really close to those values, right? We're a little bit off here, a little bit off here, and just a little bit off here, but really close. So in Excel, though, we don't have to use an approximation. We can actually use the student t distribution that this is coming from, even if we have a really high variance. With a table, you know, once we get up here, we've got huge jumps. We can't look up exactly, 600. We can't look up 4,000. So in Excel, we can look up whatever degrees of freedom we want to, okay? And get a real specific value. So from here, it's really just using Excel to be a calculator, right? We know the equation that we want, right? Either form, okay? So what we'll do is just select where those values are at in our spreadsheet. So take the sample mean, subtract from my lower bound the number of standard deviations away I want to go, which is my t value, multiply by the formula that would give me the standard deviation for my sample means, which is the square root of my sample variance divided by my sample size, right? So if I copy this down, I can then get the lower bound for the next 2 levels of confidence. The problem is the only thing I really want to change when I'm computing the lower bound for different confidence levels is the t value that I'm using. I still have the same sample mean, sample variance, and sample size. So I'm going to freeze those cells. So I can hit my F4 kind of shortcut here, or if I'm on a Mac, Command T. Now when I copy this down, there you go. I get my lower bound for the 3 different levels of alpha, or my 3 different confidence levels. Notice my lower bound is getting smaller when I want to say things with a higher level of confidence, because my confidence level should be getting larger, right? So the lower bound will get lower, the higher bound will get higher, or the upper bound will get higher. How do I find the upper bound? It's the exact same equation I have here. So if I double click on this cell, it's this exact same equation, but I'll be adding that margin of error instead of subtracting it. So I would do it this way. I go into this cell, I copy, right? Control C, or you can right click, hit copy, hit enter to get out of the cell. Go over to my upper bound, paste it. It doesn't update any of the cell references when I copy and paste it that way. I'll go over a little bit, there we go. And then I'm no longer subtracting the margin of error, I'm adding it. Right? Now when I copy this down, now I've got my 3 confidence intervals here. Okay? Any questions on that? You want to see a cell again, or okay with that? All right, so I'll show you another way you can do this. So you could find the standard deviation of your sample means first, right? So that was, we knew, just the square root of my sample variance divided by my sample size. Right? So I've got that up in a cell. I'm then going to just copy and paste these over and show you how you could build the upper and lower bound using a slightly different method. Actually, I don't need to do that. Okay. So my lower bound would simply be my sample mean minus the number of standard deviations away from that sample mean I want to go, multiplied by what the standard deviation of my sample means actually is. And I already had that calculated in a cell up there, right? So this, right, is going to give me the same answer as this, because all I really did there was I just hid the intermediate step and wrote it all in one function, right? So I knew that the standard deviation of my sample means is just the square root of my sample variance over my sample size. So instead of writing that function in, I could just reference a cell where I have that function. So 2 different ways of doing the same thing. If you want to see the intermediate step, that's kind of nice. I'm going to show you something here in just a second why it's nice to see what the intermediate step is. So once again, when I copy this down, I want everything to change except for that t-value. So I freeze these cells, references, cell references here. Right? I want to keep using the same sample mean and the same standard deviation of my sample mean. Copy this down. Notice I get the exact same 3 lower bound values, which I should, right? Hopefully. I then can do my upper bound by, once again, going into the cell, copying, hit enter to get out of the cell, paste it over here. Notice none of the cell reference is updated. It's the upper bound though, so I want to add my margin of error instead of subtracting it. Now I can drag this down and I get the same 3 upper bounds that I had. Well, I'll drag it out more so you can see out to these decimal points, right? So this is a different way of doing the same thing where it shows you the intermediate step, which is what's the standard deviation of my sample means, okay? Does anybody want to see one of the cells again, or before I keep moving here? All right. So one thing that's nice about this is, notice how narrow my upper and lower bound are here. Like with 99% certainty, I can tell you the true average female height is in between what? 64.14 inches and 64.38 inches. It's a really narrow confidence interval. Well, my sample size is huge, right? That's why. The higher the sample size we take, the smaller the standard deviation of my sample means is going to get, right? Because it's in my denominator here. There it is. It's in my denominator. So notice if I'd only taken, say, a sample of 45 people, I get kind of much wider confidence intervals. So now it goes from 63.11 to 65.39, right? So lower sample sizes means I'm not going to be able to pinpoint down where that true population mean is with as much accuracy, but if I want to keep the same level of confidence. I'm going to hit Control Z there, though. We want the original thing, not 45. We want the original sample size there, okay? All right, so we can do the same thing for sample proportions. Right? So I'm going to delete this real quick and kind of show you the same, and delete this and show you the same thing. So one of the variables I have in this data set is whether or not the individual that was in the survey was white. So 1 if they were, 0 if they weren't. If I have a 1-0 variable to find the sample proportion, all I have to do is take the mean of a 1-0 variable, which in Excel, the function for our mean is our average. So take the average of this, we get about 49% of this sample was white, right? Or identified as white. So we've got ours, if we're dealing with proportions, we no longer have to use that student t-distribution. We go back to last week, when we have proportions, we can use the standard normal distribution. We know that when we turn any cutoff value by subtracting the mean divided by the standard deviation, we know that that value, z value, will be distributed normally, standard normally, okay? So instead of t.inv, we use norm.s.inv. The area we want in the tail, alpha over 2. But remember, if I just put alpha over 2, it's going to give me that negative value. So I can just use that absolute value function. All right. Copy this down, because I no longer have a degrees of freedom I need to worry about. And notice, these values are a little bit different than the t values. Not by much, but a little bit, right? Which might not, seem like it matters a lot, but if we had really, really high standard deviations in our sample means, it would matter a lot more that we were making sure we're using the correct distribution. So I then go to my lower and upper bound. Okay. So here we're just mimicking the formula we had for the confidence interval for sample proportions. So what we had there, I need an eraser. So when we're building a confidence interval for a sample proportion, we would multiply that by the standard deviation of our sample proportion. But we knew that the equation for that was the square root of p hat times 1 minus p hat over our sample size, or our sample proportion times 1 minus our sample proportion over our sample size. So I'm just going to enter this formula in Excel, selecting on where I have the sample proportion and the sample size. So take my sample proportion, subtract the number of standard deviations away I want to go from it, or my z value, multiply by the square root of my sample proportion times 1 minus my sample proportion, divided by, and I have my sample size up here from earlier, okay? So all I did was use Excel basically to be a calculator here. So instead of entering all these numbers into a calculator, I enter them into Excel, okay? Excuse me. So on this next Excel assignment that's going to be due, I moved the date to the end of this week. When you do this Excel assignment, and I commented on people's assignments earlier, but it's from here on out, right? I need to see the work done in Excel. If you're looking up z values, you need to be using this norm.s.inv function, not simply looking them up kind of on the table and then putting them into Excel. That defeats the whole purpose of using Excel, right? Don't do this calculation by hand. I want you to enter this into Excel, okay? And I'm giving you this template file, right? This is a really good template for what you should be doing. So if I want to copy this down for different alpha values, the only thing I don't want to change is my z value. So I'll highlight everything else, hit that F4 shortcut, highlight over here, hit F4. Now nothing will change other than the z value I'm using, which is exactly what I want. I'll copy this down, get my lower bounds. They keep getting lower when I want to say things with higher levels of confidence. Excuse me, just a reminder, these correspond to the 90, 95, 99% confidence levels. Then to get my upper bound, I'll take this exact same equation. So I'll copy it. I'll go over here, I'll paste it. Instead of subtracting that margin of error, I add that margin of error. Now I just drag it down. It's really the same process as what we just did, okay? So now I get my lower and upper bound here. And notice they're pretty, when I'm dealing with proportions, especially when I have a proportion around 0.5 here, my confidence intervals can be kind of wide. You might look at this and think they're not, but remember, sample proportions, you can only ever see a sample portion in between 0 and 1. So what you're really saying is the percent of the true population proportion of people who are white in the US is between 47 and 51%. Well, it's still a range of 4%. And that's even after we took a sample size of over 3,000 people. Notice if I change this to like 45, now I can say with 99% confidence that the true proportion is between 30 and 68%. I didn't have to do any math, and I probably could have told you that was true, right? Like, that's a huge range. So when it comes to these proportions, a lot of the times, like, we can't really narrow it down unless we do have pretty large sample sizes, right? Even at 36,000 or 3,600, you know, I still have a range of 4%, if you want to think about it that way, instead of, you know, 0.04. Okay. Now, I could have done the intermediate step the exact same way as I had done up here. So I know that the standard deviation of my sample proportions is the square root of my sample proportion times 1 minus my sample proportion divided by my sample size. Right. Then for my lower and upper bound, copy and paste these over. My lower bound would have been my sample proportion minus that z value times the number of standard deviations I want to go away, or sorry, the number of standard deviations I want to go away from that sample proportion times what the standard deviation of my sample proportion actually is. Right? When I copy this down, the only thing I don't want to change is my z value, so I freeze the other cells. Right? So I get the exact same values I did before, so that's good. And then once again, to get my upper bound, I'll just copy this, paste it, change that negative to an addition sign, right? Because I want to be adding my margin of error instead of subtracting it to get my upper bound. And then kind of drag this down, right? So this first way of doing it is just entering this all into one cell. The second way of doing it was first calculate what this is, which is this equation, and then kind of enter this into Excel where you can reference wherever you put that equation, right? So it's two different ways of doing the exact same thing. Notice we get the exact same lower and upper bound here, so either way is correct, okay? Any questions over any of this? Want to see a cell again, or what? I don't know if you have any other questions related to it. No? Okay. Let's see. No. All right. All right. Well, there's no more questions on that. And I just want to mention, I do have another sheet over here that, just another example, right? It's just more of the same thing. We're not going to take kind of time to go through it in class, other than, you know, one thing we talked about, I think, a little bit last week is, what if I have two different groups? So here I had 2012 and 2016 drug death data. I built the confidence intervals for 2012 and 2016, right? Found their sample mean, sample variance, blah, 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 blah. So at the 99% level, in 2012, right, the number of drug deaths went from 1.99 to 2.9, so it was somewhere in that range. And in 2016, it was 2.02 to 2.98, right? So really what I have visually there, if I plotted those values out, they would have looked something like, here was 2012, here was the confidence interval for 2016, right? So they overlapped a lot. So I can't, even though the sample mean for 2016 was higher than 2012, if I go back and look here, the sample mean in 2012 was lower, so it was higher in 2016. But if I look at the confidence intervals, well, I only saw one sample from each year. It could very well be that the true mean for 2012 is here, and the true mean for 2016 is here. If I don't have population data, that very well could be the case, okay? So when the confidence intervals overlap that much, I can't really make a lot of statements about those two groups. If they didn't overlap, so let's say they look something like this, then I could say with 90% confidence or whatever I built these confidence intervals at, 2016, the population mean drug deaths was higher than 2012. Right? But if they overlap, I don't know. I can't say. One could be higher than the other, vice versa. Okay. So, kind of go through a little bit on the next topic to set us up for next class. Okay. So, we're going to be talking about for a while hypothesis testing, right? So with confidence intervals, we wanted to know, where is this population mean lie, right? We don't know where it's at. We're going to build a confidence interval. But we might want to be able to test specific values for that population mean. We might want to say which values we can reject more than others. And so hypothesis testing will end up giving us a little bit more power once we understand how to do it. So what we're going to do is we're going to develop a null and alternative hypothesis about where this true population mean lies. Okay. Now, the alternative hypothesis is going to be what we want to test for. And the null is essentially we're going to stack the deck against ourselves and say, all right, maybe I think that the average income in the US is less than 40,000. I'll assume, my null hypothesis is, I'll assume it's greater than or equal to 40,000. Right? I'll assume the opposite of what I believe is true. And what I'm assuming to be true, the true state of nature, will be my null hypothesis. So then I go out, I take a sample. If I can find sufficient enough evidence that goes against that null, I'll reject it. If I don't have sufficient evidence, I won't reject it. Right? So kind of the idea here is, let's say I want to test for whether or not the average mass market beer has a lower ABV than Bell's Two Hearted, which has an ABV of 7%. So what I want to find is whether or not this average mass market beer, or the mean for mass market beers, the ABV is less than 7%. So I might say I assume it's greater than or equal to that. Right? If I then take a sample and I see a sample mean of 4.5, well, that does not support kind of that null. That null is I was assuming it was greater than or equal to 7%, right? I stacked the deck against myself, but I saw 4.5%. Well, that's definitely not greater than 7. So this is evidence that goes against that null hypothesis being true. So is that strong enough evidence to be able to reject what I assume to be true? That's kind of the end goal of what we're going to be doing with this hypothesis testing. I have some assumed true value about this population mean. I find, I go out, I take a sample, I find a sample mean that's inconsistent with that. Is it inconsistent enough where I can say that null hypothesis is wrong? Okay. So there's really going to be kind of three. Oh, that's the next slide, sorry. So just to kind of some notation, right? This null hypothesis we'll write as H subscript 0, alternative H subscript A. So the null hypothesis is going to be the assumed true state of nature, and the alternative hypothesis is essentially what we're going to try to test for, or what we're trying to find. And these two things are complements, right? So if I say, the null hypothesis is that it's greater than or equal to 40,000, the alternative would be that it's less than, right? They're complements here, okay? So we're going to have three kind of different scenarios. Once I get my sample evidence, so let's say let's do a different one. Let's say I assume that the average income in the US is 50,000. If I go out and I take a sample and I see that it's, 45,000, right? So if in fact, what I was assuming is true, that the true mean for income is 50,000, well, one thing I know is true about the distribution of my sample means is it would be centered right around whatever that population mean is. So if I assume that the population mean is 50,000, the likelihood that I see 45,000 isn't very high, right? So that would be evidence that goes against, would go against this null, because it's very unlikely I see something that far away from the mean, if in fact the mean was 50,000. So here I would have found evidence that strongly went against my null hypothesis, and I might be able to reject it. Excuse me, but what if I took a sample and I saw 49,900? Well, it's not 50,000. It is evidence that goes against the null, but it would be a pretty likely sample mean for me to see if that, in fact, that was the true mean, right? Because values near the mean should be more likely for me to see. Right? So that would be an example where I found evidence that goes against the null, but not enough evidence, so I would fail to reject or accept the null hypothesis. Now, we don't really want to say we accept it. We technically should always be saying we fail to reject. And then the third, which is not really interesting, let's say I assume that the sample mean is 50,000, let's say I assume the population mean is 50,000. I go out and take a sample and find a sample mean of 50,000. Well, that supports the null, so I'm definitely not going to reject the null hypothesis there, right? So that's kind of our third potential outcome. So we'll go through this analogy. I think hopefully kind of clarifies things a little bit, which is, what if we treated like a criminal court case, just like we would set up a null alternate hypothesis. So what are we trying to test for in a criminal court case? Whether or not the person is, if I can get this to work. Oh, there we go. Guilty, right? You're in a criminal court case because they think you're guilty, or they're trying to prove that you're guilty. Well, if they're trying to prove that you're guilty, remember we said the null hypothesis would be we assume the opposite is true and stack the deck against ourselves. So if I'm trying to find that someone's guilty, the null hypothesis, I assume that they are innocent, right? Which is what we do in a court case, right? You're assumed innocent until proven guilty. Well, hopefully, right? Which makes the alternative the complement of that. If the null is that you're innocent, the alternative is the complement of that, which is you're guilty, right? Or that's what we were trying to find, test for. So what if we have sufficient enough evidence? So, what if I go out, kind of our sample evidence here is we're not looking at a sample mean, but we find, oh, you don't have an alibi. The person had a life insurance that would have paid out to you. We found your DNA at the scene of the crime. Like, if we find enough evidence that goes against what we assume to be true, which is that you're innocent, well, then we reject that assumed true. We reject that assumed true state of nature. We reject that you're innocent, and you go to jail. Right? If we don't have enough evidence, right? Maybe you didn't have an alibi, but there's no motive. They didn't find any DNA. There's not enough evidence, right, to go against assuming that you're innocent. Well, then we fail to reject it. We just continue to assume you're innocent. Right? So if the glove doesn't fit, you must acquit or fail to reject the null in this case, right? So that kind of helps us set up how we think about this null and alternative hypothesis. Next class, we're going to look at, we have different types of tests that we can do for the population mean, okay? So we'll kind of start here on Wednesday. We'll get out a little bit early today. We'll talk about the different types of tests, how we do things differently, how we eventually get to a point where we can reject the null hypothesis or we fail to reject it, right? Okay, so you should have everything you need now for the Excel assignment to finish it by the end of the week, end of the day on Friday. You might have been able to kind of piece together some of it ahead of time because we had done this one in class, and it's kind of similar for the proportion one, but you're using a slightly different equation. So I know some people already started emailing me where they were kind of able to like work their way through this part of it. But now I've shown you how to use that t.i and b to build it for when you only have the sample variance. You should have everything you need to kind of complete that assignment. Okay, so start working on that early this week so you can get questions out of the way. Email me. If you want to set up Zoom meetings, we can do that. Other than that, if there's no more questions, then I will see you guys on Wednesday.